Next talk is the importance of a silicic magmatism on the moon, and the speaker is Justin Simon.
Thanks. So yeah, as advertised, I'm Justin Simon. I lead the Center for Isotope Cosmochemistry and Geochronology at the Johnson Space Center. And I wanted to, before I got into my talk, I wanted just to expand the motto that we were throwing around yesterday about science enabling exploration and exploration enabling science. And to include missions that include sample return. And so this is, I'm a sample-based science, as Lars is, and a number of other speakers today. But this is definitely a project that piqued my interest because of mission-related science, and was only possible by mission-enabling sample return. So the peak in my interest to study silicic magmas on the moon comes about by some of these recent remote sensing studies that essentially suggest there's substantial amounts or regions of the moon that have high silica rocks. And we don't have actual samples directly sampled from some of these geomorphic features, but we do have samples that are probably consistent with those compositions in the lunar sample suite. And this is an important point of the talk. The main point that I want to make here is that we expect that these silicic magmas are an important reservoir for volatiles. This is an expectation going in based on terrestrial samples. And so if we understand the generation of silicic melts, their ascent and extraction from the interior of the moon, the timing of that, we will likely understand sort of the distribution and the budget of incompatible elements like, or molecular species like volatiles, but also the important heat-producing elements. So before I get into talking about the samples and specifically, I would like to just take a step back and talk about origins of silicic magma. There are essentially three main hypotheses for generating these high silica melts. The first is extensive fractional crystallization followed by silicate liquid miscibility. That is, after extensive crystallization, two melt phases become stable. One that's silica rich, and that is the suggested silica rich melt, and one that's iron rich or more basaltic. One problem with this mechanism is that thorium actually is known to partition with the basaltic or the iron-rich melt. And that's a problem because when we look at the high silica-rich rocks on the moon, or in general, we see that thorium is in the high silica-rich rocks. Another problem that I just mentioned for this mechanism is that this mechanism is not very efficient. That is, you need a lot of fractional crystallization to distill a little bit of silicate-rich melt. And now that we're seeing more extensive amounts of silicic magmas on the moon, and we're finding them distributed all over the surface of the moon, all over, but in greater regions, this very inefficient mechanism is less likely. So the second mechanism that I wanted just to introduce, generically speaking, is the mechanism by partial melting. So this is the opposite end member. The fractional crystallization mechanism is you're distilling, and the last bit is enrichment of the incompatible elements, including water or other halogens, and halogens, excuse me. This one is just the first melts of a rock, in this case, probably the pre-existing crust, where those incompatible elements are dissolving in or going into your first melts, and so then you're getting an enrichment of these incompatible elements. This is a schematic from Justin Haggerty showing essentially. This is in his vision here. He's inducing an impact event that's producing a basin that's causing basaltic underplating underneath the crust, which then adds heat to the crust, which then melts the crust and then produces these rhyolitic or silicic rocks. And so then the third mechanism for producing silicic melt from the moon is essentially differentiation of an impact melt sheet. So you have a large melt that's produced, again, from pre-existing crust, and as it crystallizes, it ultimately concentrates waters, the incompatible elements, and halogens. In order to, again, the reason that I'm interested in these silicic melts on the moon is that it is a dominant reservoir for volatiles. And so in order to understand the history of volatiles for the moon, perhaps the redistribution of these volatiles, it's important to understand when these magmas were forming. It also is interesting or important to understand how these magmas used to use chronology to differentiate some of these various mechanisms that I just introduced. So based on the zircon ages that are obtained from zircon that are contained in these types of rocks, David Kring showed a version of this early yesterday. We know that we have crystallization ages from, or zircon ages from about 4.3 to about 3.9 billion years ago. It's unclear, however, if these silicic magmas were generated over semi-continuously over this period of time, or if it was more punctuated, and if it was more punctuated, by what. So basically the approach that we're taking is looking at, again, Apollo return samples. This is an image of one of the more famous ones studied by Paul Warren from the Apollo 14 mission return. And most of these samples are from areas in the PKT, and our job is essentially to mine either samples that have been extracted from the lunar collection and studied extensively, so there's not a lot of material left, or to find new samples. And this is actually a lot more challenging than we thought. Of course, we'd like to return and sample these samples from the moon if we could. So before I get into some of the data and some of the actual samples themselves, I just wanted to provide a little bit of a nuts and bolts description of how we go about doing this. It's a lot of coordination. So we either, like I said, use samples that people have already extracted. For example, this breccia here from the Apollo 14, 14321, and we work with that material. Or we are beginning to use a micro CT to image larger breccias from the lunar collection to identify potential clasts that we can then use that data to request these samples, or request that the CAPTEM, the allocation working group, would then slice these precious samples and extract some sample for us for this study. After we've gotten the materials, either the residuals or new materials, we then go through a series of sample preparation techniques, including using focused ion beam milling and then extraction, so that we can get the sections that we're interested in. And these are then characterized by an array of sort of preliminary analyses, including scanning electron imagery, electron probe analyses, and micromineralogy by TEM, or transmission electron microscopy. All before we get into the real analyses, that is measurements of volatiles by ion probe and or chronology using some of the types of techniques Lars was talking about, these conventional systems. So I'm going to next discuss a number of the types of clasts. This is a work in progress. We are essentially at the point of determining the different animals in the zoo, if you would. And some of them we've studied more extensively, but we still have about 60% of our rocks, maybe 70% of our rocks that are essentially just looked at visually. So this is a representation of a class type. It's obviously an igneous texture. Here we go. This is a false colored image showing in red, showing potassium, which is one of these incompatible elements. And that potassium is residing in potassium feldspar. Potassium feldspar is not a common mineral in most of the lunar materials, but very common in silicic rocks. So you can see this is a series of, having laser issues here, a series of images showing enlarged and more enlarged regions. And you can see this is a 2 feldspar plus a silica phase class, typical of a granitic material. This is a second type of material, it's slightly different. Again, we have a high abundance of alkali feldspar. In this case, I'm just showing us some of the preliminary analyses for this class here. Again, we have the two feldspar, potassium feldspar and sodium feldspar. You can see here is a tornado diagram with the feldspar end members. So you have calcium, sodium, and potassium end members, and you can see a lot of the feldspars are indeed potassium. Here's the fib section where we pulled out a bit of this sample. And this is not an analysis that I did myself, but based on this fib section, my co-author was able to use the diffraction pattern in the TEM to go about evaluating the crystallization history, the rate of crystallization of this feldspar. So based on this micromineralogical characterization, he concluded that these feldspar are forming quite rapidly. So either in a very shallow and possibly even in a volcanic environment. This is an example of sort of the classic silicic class that you see in lunar samples. Not, again, very rare, but the classic one, the granophyre. And what you see here, again, potassium feldspar, and you see both textural and compositional variability that suggests that it quenched quite quickly. Probably as a product of rapid crystallization of a melt. And then finally, our, I guess, fourth or fifth end member, or not end member, but type in this zoo of silicic class is this class, which is got 3 minutes. Oh, great. I'm in trouble. Okay, so coarse-grained, I didn't start 3 minutes late. Coarse-grained or coarser-grained two feldspar with silica. Again, the microstructural work suggests that this is probably cooling fairly rapid, but slower than the granophyres. So I just wanted to highlight two classes that we've done more detailed work on. A true granite that I got residual material from the Apollo 14 321, and a granitoid class from the Apollo 15 that's a creepy, from a ore creep composition Lars was alluding to before. I won't go into the details here of how we go about this, but just to let you know that it takes quite a bit of work, and you have to be fairly careful. I'm going to just highlight the potassium-calcium system. This is an isochron, very similar to the type of data that Lars produced for samarium neodymium or for rubidium strontium. And the point here is that you have these mineral fractions that you measure, and then you can produce an age. In this case, when we compare this age to the rubidium strontium age that we determined for the same class and pre-existing uranium lead zircon and samarium neodymium work, we find excellent concordance. And so this age is about 4 billion years old, plus or minus tens of millions of years. So that gives us confidence that this rock is about 4 billion years old. But the thing that I wanted to emphasize that's a bit unique about the potassium-calcium system is that it's not a trace element parent-daughter pair. It's a major element parent-daughter pair. And what that provides, in addition to the chronology, is actually insight into the source of this rock. And so in this case, it's all about the intercept. And so this is the regression. If you look at this variability and compare it to the initial of the moon, and then allow for the ingrowth of the daughter from parent decay, you can model what the potassium-calcium ratio at the formation of this granite was. And if the source of this rock was 4.5, the source of this granite was more like an andesite. So that's a unique and new result. Now, I might get into that in a little bit, but I'll move on to, we can take this just one step further. If we look at geochemical data, this is terrestrial data, but if we look at geochemical data, this is from the NAVDAC data set, you can plot up all types of silicic rocks and make a comparison to this source rock. And so what you can see is this is the potassium-calcium inferred from the source, and if you then look at how it intersects this large data set, you can see approximately, as shown in this histogram over here, what the composition of that source rock was in terms of silica, which is something that we're more familiar with. So clearly, again, something that's approaching about 78% silica. Okay, 2 more slides.
We don't have time. Just solve. Finish off.
Okay, well, I just wanted to say a bit about the last class that I worked on. This is volatile analyses done by ion probe. These are volatile images, or image analyses of these volatiles. And what we see, this is not like the apatite work that's typically done, but it's actually done on anomaly anhydrous minerals. And so we're looking at, again, alkali feldspar. And what we found is about 20% water in these alkali feldspar, which doesn't sound like a lot of water, but actually when you do the partition coefficient calculations, what you find is that it's about 1 weight% water in the melt. So again, water is residing in the rhyolite. And this is a completely distinct result from what we see in the apatite, which we now know is quite the apatite data are quite misleading. And so if this is a general result for granitic magmas on the moon, then the moon was dehydrated by silicic magmatism by about 10 weight%, approximately 4 billion years ago.
You don't need to read this.
No. All right, sorry.
Well, that's okay, Justin. Thank you very much.
Unfortunately, we really ran out of time for questions, but I'm sure Justin will entertain questions during this session and following this session during lunch. Thanks again, Justin.